Welcome back. I'm Professor Plett at Bakersfield College, and despite the facial hair, I am still the same person. Did a little bit of no shave November and haven't gotten around to getting rid of it yet. But today I'm going to talk to you about something different than what I talked about last time. Last time I talked about a center of gravity and center of mass. This time I'm going to talk about something related to electricity. And this particular thing I'm going to talk about today is something called a thermocouple. Now, those of you who have done any sort of baking in the last couple of weeks, or perhaps in the weeks to come, may be using a oven or some other device that has a digital readout of whatever temperature you're baking at. And if you've ever wondered why you're able to know what the temperature is to any degree of accuracy with those things, this piece of technology is the answer to doing that. And it comes from a comparison of how we measure temperature at different ranges versus a standard thermometer. Now, if you think about a standard thermometer, you might think about one of these things. It's a liquid-based thermometer, which is pretty nice and sensitive for all of the intents and purposes that it is designed for. However, if we take a look at the temperature scale on this thing, you have about up to 100 degrees Celsius, which in Fahrenheit, since we're Americans, is about 212 degrees Fahrenheit. Now, most things involving baking usually require something in the neighborhood between 300 and 400 degrees Fahrenheit, which is not in the standard operating temperatures that this is designed for. So the question then becomes, how do we measure temperature at these ranges with any degree of accuracy? Enter the thermocouple. And the thermocouple, just to describe what it is two pieces of wire that are different kinds of metal that are joined together at a common point. Now, why is that interesting? And how is that supposed to relate at all to temperature? Well, it has to do with something called the Seebeck effect, named after the scientist who discovered it. And what Seebeck discovered is when he connected two wires of two different metals and then measured the electric potential or the voltage across them, he discovered that indeed they did produce a voltage. And what's more interesting is that when you change the temperature at the junction between them, when you change that temperature, the value of the voltage changes. So if you decide to put a high temperature at this junction, you get a higher voltage. So you'd have a voltage associated with that higher temperature. But if you decide to choose a cold temperature, you'll have a voltage associated with that cold temperature. You'll see that the voltage changes as you adjust the temperature. And now I think you can see why this is a valuable piece of technology, because what this does is, if you are basing your measurements on metals, metals are way more heat resistant and capable of withstanding significantly wider ranges of temperature. All you need to know is, how do you relate voltage to temperature? And luckily for us, we discovered that the relating factor to these things is linear in nature, meaning that if we take a graph of measured temperatures and voltages, you would produce a straight line going from low to high. And you'd have a nice straight line relationship that links those two things together. Now, that's all nice, well, and good that this works. But in order to be a proper science demo, I should explain why it works. So why does it work? Well, what it comes down to is what is inside of these metals. So I'm just going to draw a tube here to represent a piece of metal. And inside of that piece of metal, there are a lot of little particles known as electrons. And these electrons are what carry charge through a metal. This is why metals are so proficient at passing current or electrical charge. And what happens is that these electrons have a little bit of freedom of motion to them. They have the ability to move around a little bit. And what happens is, if we increase the temperature on one side, what happens is that the electrons pick up that extra thermal energy and they can move much more than their counterparts, which are substantially more limited in their motion because they're at a colder temperature. So what is the effect of this? The effect of this is if we take a look at the boundary between these two sides, we'll see more electrons moving in that direction. And that is something that characterizes an electrical potential. And this is something that we call thermoelectricity, using a difference in temperature to stimulate electrical flow of charge. And that is what the thermocouple is based around. It just takes advantage of the fact that if you use two different metals, you can more carefully guarantee and standardize the effect that you see here. And if you'll stick with me for a few minutes, I'll actually show you some of these thermocouples in action. All right, so here over at my workstation, I have a voltmeter hooked up to a copper wire, which I'll first use to help demonstrate this idea of thermoelectricity. Now, the main star of the show is going to be the thermocouple, but I want to show you how thermoelectricity works using a very large change in temperature. And to do that, I'm just going to take a soldering iron gun, and the tip here, when I turn it on, can get up to around 500 degrees Fahrenheit, which is about 200, 250 degrees Celsius. And what we should see, if I do this correctly, is that placing the hot iron tip near one of the measurement points should produce a change in potential. It's small here, but I think you can see that the number on the voltmeter has indeed changed. Now, I can't sustain that for very long because most metals are indeed conductive, and copper is no exception. So the result of that is, after it's exposed to that heat for a long amount of time, that heat will spread out, and then you'll lose that thermoelectric effect. And this is part of the reason why using two wires is a little bit more effective, because you don't have to, you can choose metals that are less thermally sensitive. Now I have two thermocouples here made of two different materials. One is made out of a lead alloy and copper, and then this other one is made out of steel and copper that have been fused together using the soldering iron. Now, what we should expect to see is that if we take the two ends of this, clip them together, and then stick them in two different temperature sources, we should see that this voltage will change. It looks like I need to stick this down the other way in order to make sure that it will measure more easily. There we go. Now I'm just going to plop it in this boiling heat bath, which we can assume is at 100 degrees Celsius. And we do indeed see that there's a potential produced. It's very small by comparison to what we would expect with most thermocouples, because most thermocouples have chosen materials that amplify this effect. The two materials I have chosen are not ideal, but they can indeed show that it works. And now if we move it over to the cold bath, we should see that this potential will change in the other direction. Right now we have negative 0.2 millivolts. And if we move it to the cold, we see that it has gone away. And whoops, gotta get this in camera here. It has gone away as a result of that change in temperature. I'll try that again just to see if we can get a better look at that. So first, in hot, we get 0.2, 0.3 millivolts. And then when we move over to the cold, we get positive value for a brief moment before it disappears. And this should work for any two metals that we give it a test with. So that is the steel and the copper. And here we have the copper, and I think it's a lead alloy because it's so pliable. So put this in. We again see the effect. We put it to the cold. You see the effect goes away and even goes the opposite direction. Now, a standard thermocouple will produce much higher voltages than this because they have chosen materials specific to this purpose. But even though this is a pretty simple, unideal demo, we can indeed see that the effect works. And with more careful data taking, we could indeed make that kind of low-high graph that we talked about, and then use that to actually determine what temperature we are at when we are using our ovens and perhaps measuring temperature using a meat thermometer or something like that. So I hope you found this interesting and now have a better appreciation for how the stuff in your home works.